Welcome to Heart Disease Classification in Python. In this beginner lesson, we will explore how to use Python to analyze and predict heart disease risk. You will learn about variables, data types, and how to work with real-world datasets. By the end, you will see how these basic building blocks combine in a mini project. Running the cell now. We need to set up our coding environment to avoid distracting warnings. This comment tells us what we are about to do. Importing the warnings library helps us hide unnecessary warning messages. We turn off most warnings to keep the notebook output clean and easy to read. Running the cell now. Keeping the output tidy makes learning less stressful. Let us make it a habit. What is classification? Classification is a way to sort things into categories. For example, predicting whether a patient has heart disease is a classification problem. You will see how we use Python to help solve it step by step. Running the cell now. Let us try making variables. A variable is a container for information. Here, we are saving a person's age. We mark this line as a comment for clarification. We store the number 29 in a variable called age. Running the cell now. Try making a variable for your favorite number. Variables can store many data types. This helps us model real-world data about people. Another helpful comment to organize our code. We give the name Sam as a string, meaning text inside quotes. This variable saves true or false information about heart disease for our person. Running the cell now. What other pieces of information might be useful to keep for each patient? Lists and dictionaries, storing more information. Python offers lists, like a shopping list, and dictionaries, like a contact card. Dictionaries let us match keys to values, just like name tags with information. Running the cell now. Dictionaries use curly brackets to organize information and keep it together. We use a comment to explain the code here. We start a dictionary to store patient data. The name key holds the string Sam. The age key holds a number for how old our patient is. We use a true or false value to track heart disease risk. We close the curly bracket to finish the dictionary. Running the cell now. Try changing Sam to another name to see how it works. We can look up values by their names, which are called keys. This comment reminds us what we are doing. We print the patient's name using the key from the dictionary. We print their heart disease status using its key. Running the cell now. Try accessing the age of the patient yourself. If information might be missing, we can check first. This comment reminds us to be careful with missing data. We look to see if the cholesterol key is in our dictionary. If it is, we print the value. If the key is not found, we show a message instead. This avoids errors that stop our code from running. Running the cell now. Careful checking helps prevent bugs. Can you add a cholesterol field now? Working with real data. Next, we will load a real heart disease dataset to practice our new skills. We will see how data for hundreds of patients is stored and explored. Running the cell now. Let us read data directly from the web using pandas. Pandas is a powerful tool for working with tables of data. This comment marks our setup section. We import pandas and call it PD for short. Here is the web address for our heart disease dataset. We read the CSV data into a table called heart_data. We check the data's shape, or size, in rows and columns. We show the first few rows to get an idea of what our real data looks like. Running the cell now. Data can look very different from what you expect. Looking at it is always a good first step. The target column tells us if a patient has heart disease. The comment highlights our goal here. We check how many patients have heart disease versus those who do not. Running the cell now. Notice if one category is much larger than the other. This affects prediction balance. Examining numbers such as averages or minimums offers clues about the data's story. This comment shows we are exploring our data. Describe gives summary stats for all numerical columns. Running the cell now. Finding strange or surprising numbers can reveal errors or interesting details. To check if our model works, we need to split data into training and testing sets. This line notes the code's purpose. We import a tool to split the table easily. 80% of data trains our model, and 20% tests it. Setting random_state makes the result repeatable. We print out the number of samples in each set. Running the cell now. Splitting ensures our model does not memorize the data but learns patterns. Building a simple rule. We can use rules to predict heart disease in an easy way before trying machine learning. Let us see what happens if we guess no for everyone, and compare it to guessing yes for everyone. Running the cell now. Let us test what happens if we always guess no heart disease. We note the intent again with a comment. We create a prediction column set to 0 for no heart disease. We measure accuracy by comparing predictions to actual outcomes. We print out how accurate this simple rule is. Running the cell now. Try changing the prediction to always 1 or yes, and check what happens. Now we use age for our prediction. We guess that over 50 may mean a higher chance. Here, we try a simple rule using real patient information. We make a prediction that sets to 1 for older patients. Lambda simplifies our condition. We calculate accuracy the same way as before. We see and print the result. Running the cell now. Think about other features that might help us predict even better. Using machine learning. We can use a machine learning model to find patterns we might miss. Let us use a decision tree, which splits data by asking simple yes or no questions. Running the cell now. A decision tree model learns patterns from past patient data. We show that we are moving to a real machine learning model. We import the decision tree from scikit-learn. Features are all columns except target, which is what we want to predict. We create the classifier and set a fixed seed for fairness. We train our model using the training data. We predict the heart disease values for our test set. Why do we compare predictions to actual answers? We print the decision tree's performance. Running the cell now. Notice if this accuracy is better than our handmade rules. Let us use our model with your own numbers. Enter realistic values for each question. We ask for age using input for interaction. We collect sex, 1 for male and 0 for female. Chest pain type has values 0 to 3. Resting blood pressure is a common number in checkups. Serum cholesterol measures fats in the blood. Fasting blood sugar checks if it is above 120. Resting ECG can help reveal heart issues. Maximum achieved heart rate gives clues about health. Exercise-induced angina is another warning sign. We ask for the value of ST depression. Slope of ST segment is a heart feature. Number of vessels colored relates to blockages. Thalassemia relates to genetic blood disorders. We combine all answers into one list for our model. Let us predict if the given values show risk. If the result is 1, there may be heart disease risk. Otherwise, our model predicts no heart disease. Running the cell now. Try different combinations to see how results change. Feel free to pause the video and experiment. If you have not already, please like and subscribe for more lessons. Good code checks for missing or blank values that could cause problems later. Checking for mistakes in your data is always worth the small extra effort. Here, we count how many missing entries are in each column. Printing them gives us a simple overview. Running the cell now. Catching missing data early prevents surprises later on. Sometimes, the model rejects data if the shape or format is wrong. This comment reminds us mistakes are normal when learning. We try to predict with only one number instead of all features. Catching the exception, or error, gives us helpful feedback. Printing the error makes it easier to understand what happened. Running the cell now. Mistakes are part of learning. Errors help us improve our understanding. Extra tips. Always start small and test each part. Print often to check your progress. Try swapping methods and comparing results. Running the cell now. Can you improve the model? Limiting tree depth can stop overfitting. See what happens when we limit the decision tree to 3 levels. We train a new model on the training data. The score method quickly shows test accuracy. Print the result to compare with our earlier tree. Running the cell now. Try deeper or shallower trees. Which setting works best? Sometimes less information can be powerful too. Here, we use only 2 features to predict. We set up and train a decision tree with just age and cholesterol. We teach this new smaller tree on the training data. Predicting with just 2 features helps illustrate model simplicity. Finally, we print the new accuracy. Running the cell now. Do not forget to compare numbers. Is this model still useful? Recap, what have we learned? You can make, read, and update Python variables. Work with data dictionaries and lists. Explore real datasets using pandas. Test prediction rules and a decision tree model. Try your own patient example. Every project starts with simple steps. Keep going. Running the cell now. Next steps and thank you. Try rewriting parts of this notebook with your own data. Practice with different datasets to get comfortable. If you learned something today, like and subscribe on YouTube for more fun Python lessons. Running the cell now. Great job! Do you want to try building a new project using what you have learned?